In this video we're going to do a review on exponential functions and rules, stuff we should already know. So we can just see an exponential pattern here. They've used an example to do with population over time, and we can see that with the growth factor 1.014 constant and a starting value of 6.707 billion, we can see an exponential pattern. In each case it's a multiplier of that same 0.014. In general we have an exponential function suited to this particular model where t is the variable. So remember, the exponent or the index is the independent variable in an exponential function. So a base exponential function is a to the x, but it might be ab to the x. Often it is, where a is a starting value, b is some sort of growth factor or multiplier, x is that variable. Sometimes it's a t or some other thing. F of x can also be known as y. So those symbols change, but the form remains the same. And interesting to note, and we're going to have a look in our further work why this happens, but if you remember your index laws, you'd probably be able to work it out yourself. If we plot the graph of those two, well, of course they look different because the bases are different, but there's a certain pattern. It's got a table of values, and below the table of values we've got a graph. And if you pause the video and have a close look at the graph, you can see that it's not just two random graphs. There's actually some sort of pattern there, and it's to do with the relationship between the two bases or the two growth factors. These laws for exponents, or index laws in other words, should be familiar to you. Make sure you pause the video and take down any that you have forgotten. Remember, the base is the same in all cases, hence the a. And we can see some of the work we did last time around. For solving these, we're going to look at example A and then example C. We can see 25 to the power x equals 125 to the 3x minus 1. One way of solving this is to put them to the same base. And using our index laws, 25 is 5 squared and it's raised to the x, and using our index law we have 5 to the 2x. You may need to revise the video back a few seconds to find that previous index law that we just looked at. On the right hand side of the equal side we have 125 is conveniently expressed as 5 to the power 3, and that's raised to the 3x minus 1 from above. We do what's called equating indices because the bases are the same left and right, so we just get the two indices left and right and we set them equal to each other, and we solve an equation, and x is 3/7. Looking now at example C, we have 2 to the 2x plus 8 equals 6 times 2x, and we can rearrange that by finding a quadratic. So making the right hand side equal to 0 by subtracting that term there, we get a quadratic because we can replace 2 to the x with a z, and you may need to pause the video to have a closer look at that. Then we have a quadratic which can be factorized. If you couldn't factorize it, you can still use a quadratic formula, and we can find solutions for z. And remember, we didn't have a z originally, we had 2 to the power x, so we need to substitute back out, and it's important to find solutions for x. That's what we're supposed to do in the question. Last time around we did a bit of work on logs, or the common logarithm. Typically, if not stated, we understand that it's base 10 logarithm. Sometimes it is stated just like there, but remember, converting between index notation and logarithms is a process where if we have 10 to the m equals x, then m, the index, becomes the answer, and we have a base of 10 here, so we have a base of 10 here, and m equals log of x to base 10. That's a conversion between the two forms. It's the same information, one's just converted to a different form and vice versa. So that's the conversion process which we saw last time around. Log laws which we developed last time around, if you've forgotten these, very, very important to pause the video and take these down, but these log laws are very important. Log of a product turns into a sum of each individual base. each individual part, I should say, not base. Log of 1 on x equals x to the negative 1, which is negative log of x. The quotient, log of 1 is 0, and the log of x to the n becomes n times log x. Log of 10 to base 10, if it's base 10, equals 1. Any log which has these two numbers the same comes out as 1. And 10 of log x equals x. All work from last year. Important we copy these down. Thus, to finish off, solve the following equations, correct 2 decimal places. Okay, using calculator only as a last resort, please note. If we've got the first one here, 1000 to the x is 81. What we've got here is replacing the 1000 with 10 cubed, and we've got 10 to the 3 times x, which is 10 to the 3x, is 81. And then basically we're rearranging it into logs, or in other words, we're taking logs of both sides to base 10. So we just left with the index there, and on the right hand side we've taken log to base 10. Alright, so we're taking logs to both sides, and they've got to be to the same base. What you do to the left, you do to the right. Then we rearrange, divide by 3, and we get 0.64. That part can be done on the calculator. The final section is this equation here, 6 to the x minus 2 to the x plus 2 equals 0. You can see that they've rearranged it there, and taking logs to both sides, notice it's to base 10, and basically using one of the log laws here to bring the x plus 2 out the front. Okay, because we can do that. There's formerly the index that can be brought to the front, and using then a further log law, we turn it into a sum, and then we regroup the equation. We rearrange in this step here. You may need to pause the video to have a closer look, and on your notes write down any questions you have for the teacher. Further log law here, where we have a quotient, and that simplifies to a 3. This simplifies to a 4, and we rearrange to find x, and then we can use a calculator, in fact, to any base we like. Once they're the same, it'll come out to approximately 1.26. Try some.